kind of carrying off of that idea, going back to the previous page, you can look, but it basically asks us first to identify if a point exists on the curve itself. So in this case, it's at 0. You start with that. Does it exist? In this case, no. And then you start getting into why is that the case. If it doesn't exist, then it could be because there's a hole in the graph. It could be because there's a vertical asymptote. It could be because there's a jump. At that point, you kind of flesh out what the reason is. But any kind of discontinuity, regardless of what type it is, will lead to a point that's not differentiable. So then we get to the second scenario involving a piecewise function. So we start the same way. We address continuity, right? So f of 0, and that's our first place to start. Because again, if it's not continuous, we don't even bother. F of 0, well, the relevant function would be this one. So, oops, do that all the time. 2 times 0 plus 2 would give us a result of 2. So we do have a point there. All right? So we know that the graph at least exists at the x value of 0. Now it's a question of, okay, in what way? Does the limits, or do the limits exist from either side? The limit as x approaches 0 from the left of my function should be the same as the limit as x approaches 0 from the right of my function. All right, the left-hand side is the top function, 2 minus 2x plus x squared. The right-hand side is the 2x plus 2. All right. In either case, when you plug in a 0, you get 2. So 2 equals 2. All right, so the limit exists. So this function is continuous, so therefore it is continuous. So it's not going to be quite as easy as the first one. Well, I mean, it's already not as easy as the first one. Because we couldn't just look at it and say, oh, it's clearly not continuous. So now what we do is we go through the derivative process. Fortunately, we have some shortcuts for that. So we don't have to do it with the limit definition. So f prime of x would be the derivative of each part. All right? So what is the derivative of 2 minus 2x plus x squared? Well, what's the derivative of the 2?
0.
0. What's the derivative of negative 2x?
-1.
Negative 2. What's the derivative of x squared? 2x. All right, so we just do it a piece at a time. The derivative of 2x is 2, and we already know the derivative of a constant is equal to 0. All right, so these are the two pieces that make up my derivative based on the conditions. So we have one of them only happening when x is less than 0, and one of them only happening if we're 0 or better. All right, so we know it's continuous. It's just a question of, do I have a meaningful derivative? If I'm going to have a meaningful derivative, the limit of the derivative from the left has to be the same as the limit of the derivative from the right. All right, what that looks like is the limit as x approaches, in this case 0, from the left of my derivative function. I want that to be the same as the limit as x approaches 0 from the right of my derivative function. All right, it won't always be the same, that's why we're testing it. All right, if they are the same, then the function is continuous and differentiable. If they are not the same, then it's continuous and not differentiable. All right. So we're going to apply the limit to the left side and to the right side. So I'll write it out. Limit as x approaches 0 from the left of negative 2x plus, negative 2 plus 2x. I want to know if that's equal to the limit as x approaches 0 from the right of just the 2. Well, I know the the limit of the derivative on the right-hand side is just 2 because it's constant. All right. Now, on the left-hand side, what would I have as my limit? Negative 2. These are not equal to one another, all right? So this tells us that we're not differentiable. At x equals 0. That's a good point. Because everywhere else it's fine. It's just at x equals 0 that we have a problem. All right, so we need to generalize this. So we think about what happened here. We have a continuous function.
Wait, what's the difference between the 0 approaching from the left and the 0 approaching from the right?
Graphically, it's exactly just that. You're following the graph from the left and from the right. But from the piecewise function, it's top to bottom is the left,
Okay.
bottom to top is from the right. All right, so continuous function, but not differentiable. But specifically, where the limit of the derivative from the left and from the right approach two different finite values.
So if it was negative infinity positive infinity, it would be a corner.
Correct. All right. Now you could also look at the graph of this, but this will get the job done too. It also depends on the situation. Piecewise functions are a little funky in your calculator, so most people tend to shy away from doing it on the calculator. But you know, there's a time and place for everything, I guess. Generally, a corner visually is when two graphs come together to form a point. So, example would be like an absolute value graph. Well, that's poor quality absolute value graph. Still, I drew it exactly the same way.
Those infinite values?
Finite.
The problem that we just did, that is a corner, right?
That is a corner, yeah. I'll give you one guess.
You're in conflict.
All right, so here are a few examples of what corners look like. They come to a point in some capacity. All right, so I have an absolute value graph, or at least an attempt at one. I have a piecewise graph where we have a line and part of a parabola, and then another parabola, or maybe some other kind of function that only looks like a parabola on that interval. But here's an example of something that comes to a point but is not a corner. It's kind of, my drawing ability is just dreadful. That was actually better, what I just did. A stray mark I accidentally produced. So if it kind of bows inward, it's not a corner. So it still comes to a point, but it's not a corner, it's called a cusp. And we'll get to that in the next page. But it's the idea that it has some sort of bowing effect. Maybe, I don't know. It's just getting worse. But it's kind of going in and then merging. So probably like the best way to do it would be like this, where it's actually merging over a small interval. That's what a cusp is versus a corner. Corner is like a sharp intersection between two curves. All right. Why is that important? Because some questions on the test will say, determine what type of non-differentiability we have here. Is it a corner, cusp, vertical tangent, or something else?
If you didn't add like these pictures and you just determined it the way we did with the limits, like how would you know which it is, just based on the definition of it?
Yeah.
Okay.
Two different finite values. For the limit, we know that means that we're dealing with a corner. We're going to get to two other cases in a minute where they're not going to be two different finite values, and we'll see what that looks like. All right, so determine if the function is differentiable at 0. Well, we address continuity first. F of 0 is equal to 0. If I plug in a 0, I get a 0. Doesn't matter that it's 0, it just matters that it exists. If I go to find the limit as x approaches 0 of this function of x squared, x to 2/3, I also get something that exists. And it happens to be the same as the evaluated function. So these two things bear out, so therefore it is continuous, and we're not off the hook, right? We want, as students taking test quizzes, things like that, we want this to fail, because that means we don't have to do any work after that. But we know oftentimes it's not going to fail. So now I take the derivative.
Is this just because it's not a piecewise function when we're not comparing
The left and the right?
yeah.
Yeah, well, also because through direct substitution, I got an answer. So that always trumps any other approach. So my derivative would be what? Power rule. Multiply power by the coefficient, reduce the power by 1.
2/3 x -1/3.
To the negative 1/3, exactly. All right. So I could rewrite this a little bit. It would be 2 over 3 times the cube root of x. All right. So what I would need to do here,
Why is it negative 1/3?
because 2/3 minus 1 is negative 1/3. 2/3 minus 3/3. All right. So what I need to do now is find the limit from the left and from the right of this guy, going to whatever I suspect the location of non-differentiability would be. But in this case, I don't need to suspect, they told me. So I need the limit as x approaches 0 from the left of my derivative. And I'm going to compare that to the limit coming in from the right. And see what the relationship is. Right? We know it's going to involve infinity and subcapacity, only because the last one I said you have to have two unequal finite values. If the two values were equal to each other, then it would be differentiable, so it's not that. So obviously some kind of infinity must be in play here. Right? At this point, I really don't care very much what method you use. You can do substitution. If I plug in, coming in from the left, plug in a negative number for this. What do I get? Do I get a positive number or a negative number? Negative, right? So if it's going to one kind of infinity or another, and I now know it's going to be a negative number, it's logical to assume that it's going to be negative infinity. If I plug in a positive number here, what kind of number would I get? A positive number, all right? So positive infinity.
Why are we plugging in infinity?
we're plugging in just some numbers that are close to 0 from the left and from the right to get a sense.
Oh, okay.
All right, but all we need is the nature of the number, because if I know it's going to some kind of infinity, I just need to nail down which one it's going to, positive or negative. That being said, you may not like that approach, and that's fine. We've talked repeatedly about how to find derivative graphs in our calculators. So without even having the derivative, okay, so this is really important. I'm asking you to determine if it's differentiable. Technically, I did not need to find the derivative. I just need to answer this question here, really. But I could write this in general terms. I could write limit as x approaches 0 from the left of f prime of x. Limit as x approaches 0 from the right of f prime of x, without actually ever stating what f prime of x is. So I would put in, I'll use the cube root function, oh actually no, I won't. X to the, that was a different problem. 2 thirds. I don't want to see that graph. In my Y4, in case you missed it the first 14 times I did it, math 8 x y1, which you get by hitting alpha trace and then selecting y1, and then x again. I like to have it bold, but in this case I'm only going to be looking at my derivative graph, so I really don't care. Zoom 6 ought to do it. Zero is our benchmark. So from the left, where does it seem to be going? Negative infinity. It seems to be going down. I mean, we lose track of it after a time, but if you know it's going to some kind of infinity, it certainly seems like it's going down towards negative infinity. From the right, it seems like it's going towards positive infinity. So you can get it that way. I'm not limiting your use of a calculator. One problem on the test that tells you to do a limit definition of a derivative. Everything else is fair game, using whatever approach you want. All right. So, not differentiable at x equals 0. All right. Not differentiable at x equals 0. We need these two limits to be exactly the same. Bless you. Bless. Well done in one go. I like that. So the limits are not equal to one another, so it could not be differentiable. It's just a question of what kind. So what this is telling me is if we're dealing with a continuous function, and the limits of the derivative from left and right go to opposite infinities. All right, so a corner, it was the case where they were going to different, they didn't have to be opposite, but different finite values. Now they're going to different infinities, right? So opposite infinities would be the only way that that would work, right? So we're good to go there. You go through the process, if you get two opposing infinities, then it's a cusp. And on the previous page, we talked about what that looks like.
So if it says like do this using a limit definition, does that just mean we have to do like this work here?
That, with the limit definition, it would mean that you would have to come up with this derivative using the f of x minus f of a business.
Okay.
Yeah, that, I'm not gonna ask you to do it that way on the test.
Okay.
That, I mean, this is already enough work.
Yeah.
I feel like that would be overkill.
I'm a little confused on differentiable,
Like the whole concept?
I guess.
Oh, that's awesome. So,
It's like the meaning of
it means able to find the derivative at a particular point. And so, when you find the derivative of a function, you get an algebraic expression. What we're trying to determine is whether or not that expression has any meaning whatsoever. So we're going to investigate, and that's what we're doing here, investigate the derivative at particular points to see if the derivative has any meaning. So when I find, if I tried to plug in a 0 to my derivative function, I would get undefined. But undefined could mean a lot of different things. When you're talking about slopes, undefined could mean that you're dealing with a vertical line. But depending on what kind of undefined, you might be dealing with different types of situations. One of them is a corner, one of them is a cusp, and another is something called a vertical tangent, which we're going to get to in a second. Being able to flesh out that information analytically is pretty important. Right? So that's kind of the motivation behind all of this stuff. Right? And also, you know, I mean, there is the student aspect of it. Like, again, if I know something's not differentiable, then it's not something that I need to really worry about. Like, I'm not going to do math to this situation if I know that I'm not going to get a meaningful derivative at a particular point. What's the rationale behind that? Doesn't make sense, right? So that's what we're really looking at. Determine if the function x to the 1/3 is differentiable at x equals 0. All right, so clearly we're working towards a vertical tangent here because I just said it, and also it says it at the bottom of the page. So continuity. I'm just going to put a check next to that, not because we're just taking it for granted, but because this is so similar to number 3 that it's going to work out the same way. So I'm just going to save the steps. We do need the derivative.
1/3 x and negative 2/3.
Exactamundo. Very good. Which we could also write as 1/3 times the cube root of x squared. You don't actually have to rewrite your derivative. You can leave it in this form. I'm only writing it like this for instructional purposes, so that you can look at it and kind of get a sense of where the x belongs within the derivative function. And really it's just to point out the idea that, yeah, 0 is going to make it undefined. And because of that, we know that we're dealing with some kind of funkiness going on in my function. It's just a question of, well, what is it? All right. So the limit approach, limit as x approaches 0 from the left of f prime of x. And I want to see how that relates to the limit as x approaches 0 from the right of f prime of x. All right, you could do it by substituting in, or you could do the way I just showed you, which is, I think, hopefully you're coming around to that. It's a good way to do it. All right, my original function is x to the 1/3. I don't need to see that. But anytime I adjust something within a field here, so in the y1 field, it turns the equation back on. So if you don't want to see it, hit enter on the equal sign so it takes the bold font off of it. All right, so I want to see y4 because I'm looking at the derivative, and I want to see it from the left and from the right around 0. So I have y4 set up, zoom 6, and I just want to know what's going on around 0. All right, seems to be going, as we come in from the left, it seems to be going up. From the right, it seems to be going up. All right. So vertical tangent, continuous, and the limits of the derivative go to the same kind of infinity. All right, this is an example where they're both going to positive infinity, but they may both be going to negative infinity. All right, and just for giggles, let's take a look at the original function. Because I described what a corner and a cusp look like, so let's take a look at what a vertical tangent looks like. All right, it's kind of slipped in there, but, and I'll bring it in a little bit, I'll do a zoom box. A little bit better. It might be even better if I turn my axes off. All right. So that's what we're really looking at. And The idea is that it goes vertical somewhere. All right, on the interval of the graph, whatever it is, if it's closed, like it's a given interval, or some interval you determine yourself, or even an infinite interval, at some point, if there's going to be a vertical tangent, it must go vertical, all right? And actually, there's something called the ruler test. Actually, I don't know if it's called that or if I just made it up, but the ruler test would actually give you the answer to the limit questions from the left and from the right without actually finding a derivative or even looking at the graph of the derivative on your calculator. Let me just show you what that looks like real quick. So here's my function that goes vertical. There's going to be a vertical tangent here. What I'm trying to figure out is the limit. I'll call this point A. Limit as x approaches A from the left of my derivative, and the limit as x approaches A from the right of my derivative. All right, it's actually, I wonder, I don't think, maybe I can do it with this. We'll see. Yeah, I think I can. Just so the folks at home can see. All right, so what we do is we use our ruler to estimate the slope of the tangent for points that start off being kind of far away from the point in question, and slowly work your way towards that point while adjusting the slope on the ruler. All right, so I would take my ruler, maybe start off over here. It would have a slope something around like this, all right, pretty horizontal. Then as I get closer, the slope starts changing. My tangent slope is increasing. So I'm at this point and I have a pretty positive slope. So it started off at 0 and now it's increasing. It's getting larger and larger and larger. So I can continue, and as I get closer and closer to that red dot, my slope estimation is making my ruler go more and more vertical. That slope seems to be approaching what? Infinity, because it's approaching a slope that's very large. I mean, this is probably a slope of like 100. If I get even closer, it's probably a slope of 1,000, then 1,000,000, then a gazillion. So a lot of different possibilities. And so from the right, based on that, I would get a slope of infinity. And we're able to do that without having to find a derivative. All you needed was a sketch of the original graph. So from the left, you do the same thing. I have a slope here that's negative, but as I move closer and closer, my slope became 0, and now it's getting more and more positive, larger, 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 larger. What does it seem to be approaching now? Also infinity. All right, it's approaching the same kind of infinity. And if you try that with the other function, one that we did earlier, a cusp, let me just turn the ruler off for a sec. Let me just put a cusp in here. And again, it would be the limit as x approaches A from the left of my derivative, and the limit as x approaches A from the right of my derivative. All right, so I'll start on the right again. It's just easier for me with this tool. So I'm estimating the slope at a point. And so as I get closer and closer to where I think the non-differentiable point is, my ruler seems to be approaching a slope of what? Is it getting smaller and smaller, larger and larger, what? Larger and larger in what direction, positive or negative? Positive. Okay, so it appears to be approaching infinity. All right, if I come at it the other way, trace or estimate the slope with the ruler as you get closer and closer to that point where they intersect, what does my slope look like it's approaching? Negative infinity.